Hey there, everybody. Welcome back. It's time to talk about more about the mole. Today's lesson is going to be all about molarity, which relates to something called concentration, which really is all about solutions. So, ionic compounds in particular. Let's talk about those. So basically, they have definite formulas, but they don't form individual molecules. Instead, they will form something called a crystal lattice. Now, a crystal lattice is just a regular repeating structure, and an example of one is right over here on the side. Now, this crystal lattice, suppose that this is NaCl. You can imagine that each of these little purple little spheres represents a sodium, and each of the green ones represents a chlorine. So when we have a crystal of NaCl, we are not talking about one sodium atom stuck to one chlorine. We're actually talking about a regular repeating pattern where they've got a sodium and then a chlorine, then a sodium and a chlorine. And this extends out into 3 dimensions. So it's a 3-dimensional crystal lattice. Now the chemical formula is called a formula unit. And what that means is that is really just a ratio. It tells us what the ratio of positive to negative ions are. And positive ions are called cations, and negative ions are called anions. So the formula NaCl just tells us that there's a 1-to-1 ratio. For every sodium, there's a chlorine, and there's another sodium, then there's another chlorine. In actual fact, if you look at this crystal of sodium chloride, which is NaCl, you can see that in this regular repeating pattern, if you pick any one of these sodiums, take this one right here, you can see that it's actually surrounded by 1, 2, 3, 4, and then another chlorine behind it is 5, and then another chlorine in front of it would be 6. So each sodium ion is actually surrounded by 6 chloride ions and vice versa. Which is to say that if you pick a chlorine, any of these chlorines is going to be surrounded by a number of sodium ions. And that's just because chlorines like sodiums and sodiums like chlorines, and they don't like each other. So sodiums are going to try and stay far away from other sodiums. Now, we're not going to go into too much detail about this, but it's just important to recognize that the difference between this ionic compound and, say, a covalent compound is that if you take a covalent compound like water, when we say it's H2O, we're talking about it forming an individual molecule where there is one oxygen and 2 hydrogens stuck together, and they form a little unit that can float around and be a liquid and do all kinds of stuff. And if you zoom in, you would see individual distinct little molecules. So what happens when we dissolve things in water? So for example, if you take some salt and you shake it into a glass full of water, you know that eventually that solid is going to dissolve, which is to say it's going to disappear. So ionic solids placed in water will dissolve. Now, I should point out that's not true of all ionic solids. There are lots of examples that are insoluble in water, but many of them will do this. And I want you to consider why that is. So what's actually happening when you have a crystal like this sodium NaCl crystal? What happens when it dissolves? Well, water, you may or may not know that water is actually something called a polar molecule. We're going to talk more about polar molecules later. But the important thing to know about polar molecules is that they've got parts of them that are a little bit negative and parts of them that are a little bit positive. In the case of water, the oxygen is just like a little bit negative and the hydrogen is just a little bit positive. And so what happens is this sodium ion that's right there gets surrounded by water molecules so that all the little negative parts of the water molecules surround the sodium. And then sodium's happy because it's positive and it's got a bunch of admiring negative charges nearby, and it's happy. And because it's got those waters surrounding it, then it doesn't need to be around the chlorides anymore. It'll just kind of float away. Well, chlorine or chloride ion does the exact same thing, except it gets surrounded by the positive parts of water. And so little chloride ions can break free from the crystal lattice and just float away. And when the entire crystal lattice gets broken up into individual ions like this, then it has dissolved. And so this happens because water molecules have partial charges called dipoles. Now again, we'll talk more about that later. The water molecules surround the cations and the anions and basically just allow them to float away. And so when we have a solution, there are parts of a solution called a solute and a solvent. So the two parts of the solution. The solute is the thing that gets dissolved. So in this example here, we're talking about salt. But that could be anything. It could be sugar or food coloring or hydrochloric acid or whatever. It's the thing that gets put into the container that gets dissolved by something else. Compare that to the solvent. The solvent is the thing that does the dissolving. And in this case, our example would be water is the solvent. So whatever there's more of is the solvent, and whatever gets dissolved into that is the solute. And so a solution is just a homogeneous mixture of solute and solvent. And there are lots of examples of solutions, right? So like chemical ones like hydrochloric acid, or more common ones like vinegar or Kool-Aid or something like that. Anytime something is so completely dissolved in something else that we can't see the individual parts, then we're dealing with a solution. So a solute gets dissolved in a solvent to make a solution. And those words all sound similar, but they have different meanings. One thing to keep in mind is once we make a solution, once we dissolve the solute in the solvent, then those individual particles are evenly spaced throughout the solvent. It's not like you're going to have a situation where all the sodiums cluster over on one side and all the chlorides on the other side. They're going to be really evenly mixed and flowing around and moving all the time. So that brings us to this idea of concentration. Now, kind of oddly, one of the symbols for concentration are these little square brackets that you see right here. So when we're talking about the concentration of something, we put a little square bracket around it. And concentration is really just a measure of how much solute is dissolved in a given amount of solvent. Now, when we talk about concentration, we can talk about it in just sort of general terms, right? You can talk about a concentration being very concentrated or more dilute. So if we look at these test tubes on the side here, I can see this side here are my concentrated solutions, and over here are my dilute solutions. The particles are more spread out. There's less solute dissolved in it. But of course, as chemists, we need to be a little bit more specific. You can't just take hydrochloric acid that's, kind of strong and then mix it with something else and see what happens. You want to know exactly how strong that hydrochloric acid is, or exactly how strong that sodium hydroxide solution is. And if you want to know exactly how strong it is, one way to measure that is to measure it in molarity. And the symbol for molarity is capital M. And molarity, M, is really just the number of moles per liter. So if I told you that I had a solution of acetic acid that was 1 molar, what I'm telling you is that I have dissolved 1 mole of acetic acid into a 1 liter solution. Or I've done it in such a way that the proportions add up to that. So let's look at a few examples here. So what is the molarity of a 2.5 liter solution that contains 4 moles of hydrochloric acid? Now, there's a couple ways to do this, and I'm going to show you one way and then maybe show you another one. So what is the molarity? What is the concentration of HCl? And then there's 2 bits of information I'm given here. I'm told both the volume and I'm told the molarity. So I have to decide which one of those I'm going to start with first. Well, we know that when we're doing mole conversions, we always actually are trying to get into moles. That's like our starting point, or wherever we're trying to get to first. So if they tell me the moles, I'm going to start with that. 4.0 moles of HCl. And now, if I want to talk about the molarity, that is literally just the moles per liter. So one way to do that would be to just go ahead and divide it by the number of liters, 2.5 liters. And so what I would get here is 1.6 molar HCl. Remember that this molar, that capital M, means moles per liter. They're the same thing. If you really want this to look like a chain calculation, like we've been doing so far, you can do that, and it would just look like this. The concentration of HCl is equal to 4.0 moles of HCl, and then I would just multiply it by 1 over 2.5 liters. You can see that 4 divided by 2.5 is the same as 4 times 1 over 2.5. They're the exact same thing, and the answer comes out the same. It's 1.6 molar HCl. So if you want it to be part of a chain calculation, you can just multiply it by 1 over that thing. And if you want to just do it as a single calculation, well, then you can just do it as like that. Okay, so I should point out maybe that the concentration, we can define the concentration in that case. The concentration will just equal N divided by V, where the C is our concentration, and then N is our number of moles, and of course V is our volume. And remember that we're going to stick to base units, so make sure your number of moles is in moles, and your volume in this case is going to be in liters, not milliliters, for example. So what is the concentration of a solution made by dissolving 15.0 grams of calcium carbonate to a volume of 250 milliliters? Okay, so I'm trying to figure out what is the concentration of solution made by dissolving calcium carbonate. So the concentration of calcium carbonate, and calcium carbonate is CaCO3. So what is the concentration of that if I dissolve 15.0 grams into 250 milliliters? Well, I'm going to start here with 15.0 grams of CaCO3. That's going to be my starting point. And the first thing I do is I'm going to multiply it by a ratio. And which ratio I'm going to use? Well, that's going to be my molar mass. So I'm just going to do a quick calculation here. The molar mass of CaCO3 is going to involve, let's see, 1 calcium and 1 carbon and 3 oxygens. Oops. And 3 oxygens. Now I can check my periodic table. Calcium is right there. It's 40.08. So 40.08. I remember that carbon is 12.01, and oxygen, I've done that a bunch, that's 16.00. So all of those things add up to a molar mass of right around 100.09 grams per mole. That's for calcium carbonate. So going back to my chain calculation here, I've got 15 grams of calcium carbonate. I'm going to multiply that by 1 mole divided by 100.09 grams. And then I need to multiply it by another conversion factor. If I stopped there, then I would just be in moles, but I want to be in moles per liter. So this one's kind of weird. I don't really have a ratio exactly. I just want to go from moles into moles over liters, moles per liter. If I'm in moles right now, then I'm just going to multiply this by 1 over the number of liters, which is 0.250 liters. Now notice a couple things. I didn't use my milliliters, so 250 milliliters is 0.250 liters. And this might look kind of strange because this last step isn't really a ratio, but that's because I'm not trying to keep it as a ratio. I'm trying to go from moles into moles per liter. And when I multiply this all out, 15 divided by 100.09 divided by 0.25, I get 0.60 molar CaCO3. Okay. So let's do another one here. A student needs to make 100 milliliters of 0.085 molar copper 1 sulfate solution. What mass of solute is needed? Okay, so now we know how strong we need to make the solution. The question now is, how much should we start with? And this sort of makes sense. If you're in a lab, if you need to make a solution, you're gonna have to work backwards to figure out, well, how much should I start with in the first place? So the question is, how many grams of copper 1 sulfate? Copper 1 sulfate is going to be Cu2SO4. So how many grams of copper 1 sulfate? And that's going to be equal to, well, again, I've got two pieces of information here. I know the volume that I want to use, and I know the concentration that I want to use. And it might be confusing as to which one we're going to start with. But remember, whenever we do these calculations, we're trying to go through moles. Moles is our conduit to everything. And so I'm going to use the number that already has moles built into it, which is, I'm going to use this 0.85 molar number. So 0.85, and I'm even going to write that as moles per liter, just so I remind myself that that's really what molarity means. I want to be in moles. So what's the first thing I can multiply by to get rid of the liters? Well, if I have moles per liter, I can just multiply it by the number of liters that I'm dealing with, 0.1000 liters, and I can see that that first step is actually just going to cancel out the liters involved. Now again, everything we've done so far has been a unit conversion where like the top and the bottom equal each other, and so that's why we're multiplying it. This is the one case where it's a little bit different. What we're trying to do is we're trying to go from moles per liter into just moles. So I don't need anything on bottom of that ratio. There's no other unit to convert into. I'm just getting rid of the liters. So if I stop here, I'd be in moles per liter. But I want to be in grams, which means I need to know what the grams per mole are for copper 2 sulfate. And of course, that means I'm going to have to go find the molar mass. So let's do a quick calculation here. Molar mass of copper 2 sulfate. That's going to involve 2 coppers. It's going to involve 1 sulfur, and it's going to involve 4 oxygens. So if I check my periodic table, copper has a mass of 63.55, so 63.55. Sulfur, I can never remember sulfur. Sulfur is 32.07. 32.07, and then oxygen, I remember that's just 16 even. So when I add all of these up, the molar mass ends up being 223.17 grams per mole. So I'm going to take this back over to my chain calculation, multiply it in here, 223.17 grams per mole. I'm going to check my units. The moles here cancel with moles there, and you can see that I'm going to be left in grams. So that's what I wanted the whole time. So when I crunch these numbers, 0.85 times 0.1 times 223.17, I end up with 19, or right around 19 grams of copper 2 sulfate. And so that is my answer. Okay, so there's one more example here I want to look at. And the other example I want to look at is what happens when we have a dilution. So a dilution is a situation where we make a solution. We've got a solution already, and then we come along and we add water to it. Or maybe we add a whole other solution to it. And so what is going to happen to our overall concentration? Obviously, for example, if I pipette in a certain sample, and you can see this is pretty concentrated, and then maybe I make it up to a certain volume by adding water, I've gone from a more concentrated solution to a more dilute one. What I want you to notice about this right here, and this is going to help us out, there is a little formula we can kind of derive that's going to help us figure this thing out here, which is to say that, so we know that concentration is equal to the number of moles divided by the volume. Well, let's think about this situation here. I'm going to take a certain sample of a solution, put it in my flask, and then I'm going to add water. What I want you to notice is if this is solution number 1 and this is solution number 2, those two solutions have something in common. One of them is really concentrated, one of them is dilute. So their concentration isn't the same. But what is the same is the number of moles. So the number of moles in number 1 would have to equal the number of moles in number 2. If I take this formula and I rework it and I just solve it algebraically, I can see that the number of moles will equal the concentration times the volume. So I could say that the concentration of 1 times the volume of 1 has to equal the concentration of 2 times the volume of 2, which is just another way of saying that our solution is going to have the same number of moles in it. It's just going to change in concentration. And so this is something called the dilution equation. And that might be a useful one for you to kind of understand. Okay, so a student transfers 10 mils of a 2 molar sugar solution to a 250 milliliter volumetric flask and fills it up with water. What is the final concentration of the solution? Well, since C1V1 has to equal C2V2, if we take C2 as being our final concentration, then C2 is just going to equal C1V1 over V2. And so the initial concentration here of 2.0 molar, multiply that by the initial volume, which is 0.01000 liters, and then divide that by the final volume, which is 0.2500 liters, a lot of zeros there. We end up with an answer that is 0.080 molar. I guess sugar is my unit, okay? So that is it for molarity.